Great. Thank you very much for having me. It's a great pleasure and an honor to be with you. And I'm sorry I couldn't be there in person. I have fantastic memories from visits to Hong Kong. I hope I will be able to join you sometime in the near future. So I'll talk to you about our efforts on conducting polymer devices for wearables. Let me start with an introduction. The motivation for this is neurological disorders. That dictates a lot of the work that takes place in my group. This is a major societal burden in terms of DALYs, which is disability adjusted life years. It ranks the highest in the damage it causes to society. So we need to do something about this. Here comes bioelectronic medicine as a new capability that humankind has developed to act on the human body through electrical recording and stimulation. This is an example that we've all seen before. Deep brain stimulation with implanted devices here in the subthalamic nucleus. You have an amazing amelioration of the symptoms of motor disorders, of movement disorders, such as dystonia, Parkinson's, tremor, as is shown here in this example. The same technology has been applied to epilepsy, neuropsychiatric disorders, obesity, and the list is ever expanding. So this is wonderful development, great news. Where is the catch? The catch is we do not understand how the brain and in general the nervous system works. It's a very complicated machine. In the brain alone, we have an astronomical number of neurons. And although we understand how neurons connect with each other and transmit information through an action potential and then synaptic transmission, we do not understand how we go from these cellular phenomena to macroscopic behavior. Again, in the context of the brain, in order to follow that line, you combine implantables, cortical, and wearable devices to put together a picture of how cellular activity goes to network activity, goes to behavior. The opposite is also not understood. What is the mechanism of neuromodulation? If you modulate with an electric field, why does behavior change? So these fundamental limitations go hand in hand with technological limitations, some of which I have listed here. And the important thing I want to put out today is that this is limited by technology. New technologies are urgently needed to help us understand the nervous system and enable the benefits of bioelectronic medicine. So today I want to focus on wearables that are meant to address the fact that signals that emanate at the surface of the skin are small and diverse in nature. Typical bioelectronic medicine as it's practiced today is highly invasive. You use penetrating probes as opposed to cortical ones, and wearables can help a lot with this. So here we're talking about interfacing with the body without going through the skin. Initially, that might seem like a tall order, but turns out there are plenty of things you can do from sitting on top of the skin. Let me, for the sake of introduction, let me mention that the skin is the largest organ. By itself is very interesting to study. It's a barrier that protects from the outside world, but it does also plays quite sophisticated roles in regulating body temperature and synthesizing vitamin D, and so on and so forth. And through the skin, we can interface electrically with brain, heart, muscle. We can do optical interfacing. Previous talk was excellent introduction to this. Mechanical interfacing and so on and so forth. There are lots of wearables as a result of that. Some are at a state that is quite advanced. Non-invasive ones such as watches and wearables and electrodes that attach to the skin. Currently, the ones that are commercially available do mostly physical type of sensing. There is some biological sensing that is shown here, but this is moderately invasive. Here you use needles to go through the skin, so it sits in between the spaces that I mentioned. In terms of electrical activity, measuring electrical activity in the clinic, what is called cutaneous electrophysiology, you have a lot of applications, both for recording and for stimulation. For example, a recording of the brain in electroencephalography is used for diagnosing epilepsy, is used to monitor patients in coma, and a variety of other indications, electrocardiography, myography techniques that are very useful to the clinic. Stimulation through the skin is also used in the clinic, transcranial direct current stimulation, tumor treating fields, transcutaneous electrical stimulation of nerves, and so on and so forth. And the technologies are shown here. Typically, we talk about silver chlorides that are loaded with a gel and adhere to the skin, or conducting fabrics, or even metal cups that are filled with gels. So with this as an introduction, I wanted to show work on three fronts. One is to answer how small can we make electrodes and still be able to record. That's a question that hasn't been answered yet in my view. The second is, can we control from the outside the depth of stimulation? And the third is, what if we were to go beyond electrodes? What advantages do we get if we use more sophisticated transducers? So here are examples of some modern electrodes. We've seen electrodes conducting polymer electrodes being developed on textiles, metal electrodes in a fractal structure being integrated with the skin, and even tattoo-like electrodes being deposited on the skin, offering excellent conformability. There has been a lot of interest in going large area. This is an example of work where large electrodes were applied in a tattoo-like fashion to cover a large fraction of the skin here in the stump of an amputee. And these record muscle activity and can drive a prosthesis, can drive a myoelectric, as it's called, prosthesis, to do quite some complicated maneuvering. However, here the question of resolution arises. What if you were able to make even smaller electrodes and get even better articulation from the myoelectric prosthesis? This, of course, would be very interesting. How small can you go? As you make the electrode smaller, its impedance increases, and that prohibits the recording of high quality signals. For this reason, we use conducting polymers, materials such as PEDOT-PSS, which I don't think needs an introduction to this audience. These have shown the ability to conduct both ionic and electronic carriers. They're used a lot in the context of implantable devices where ions from, for example, the cerebrospinal fluid can go in and couple with electronic charges. And this gives rise to capacitance that scales with volume. This allows you now to minimize impedance by increasing the thickness of the electrode while maintaining a small footprint of the electrode that allows high resolution. So in a sense, they allow you to cheat on this area versus impedance trade-off and get reasonably good impedances, even with small electrodes. So here's one example of a device for myography. Here we made an array of 4x4 electrodes that had millimeter dimensions. So here we inkjet print silver, then we align a medical tape that is pre-perforated with a laser, and we use a gizmo that was 3D printed to align the electrodes with a tape. We use this tape as a mask to deposit P dot on the electrodes, and then after some heating and incubation in saline, we peel off the top adhesive from this tape, patterning the P dot only at the electrode area and offering an adhesive substrate surface to the skin. And we can do small electrodes with this technique, then place them on the skin and measure impedance. So this is the impedance of a large, actually 2 centimeter diameter, I believe, silver chloride electrode. As the P dot electrode is made smaller and smaller, its impedance increases, but it's still to the point where it can record high quality myograms. This is shown here. So this is on the arm of a volunteer, and we're recording myograms with respect to an electrode placed here on the elbow. These are examples of the data as different fingers are moved. And if you look at the spatial resolution, then just by looking at these still images at a given amount of time during the EMG recording, you can immediately know that you can now recognize individual finger motion from the pattern of activity as it moves on the array. And dynamical data offer much more information. You can look at muscle activity as it moves under the electrode with these devices. So these are millimeter size, and we haven't reached the limit yet. As you see, you get different information from nearby pixels, which means that smaller electrodes might be able to provide even richer information. The second thing I want to touch on is the depth of stimulation. Can we look at how deep you can go with stimulation? And this work here is in the context of small fiber neuropathy. As global incidence of diabetes increase, neuropathies, which is a comorbidity, are also increasing. Small fiber neuropathy is associated with the death of small fibers shown here in this histological images that die at very proximal to the surface of the skin. And this is very dangerous for patients because they start losing the sensation of pain, which is very important for survival, for avoiding accidents and things like burns. It is very difficult and expensive to diagnose. It's diagnosed using skin biopsies, where a punch is used to remove a part of the skin, so the patient has to go to the hospital. And then histology, where you can identify, you can stain and identify, and then measure the density of these fibers. Lasers are also used to create evoked potentials and kind of quantify the number of these small fiber endings. Again, this is very expensive, requires a patient to go to the hospital, and it can cause burns upon repeated measurements. So these techniques are not suitable with a scenario where you want to follow the progression of the pathology. Electrical stimulation would be very convenient to use. Unfortunately, it is unselective. even if you penetrate the skin with microneedles, trying to locally excite, you do get quite a lot of spreading of the stimulus. And what you need to do is to stimulate only these small fibers and not the other receptors that are a bit deeper in the skin. So a couple of years ago, there was a paper by an Italian group showing that if you make interdigitated arrays, then you can control the depth of stimulation by controlling the size and the spacing of the electrodes. Then you can control how deep into the tissue the electric field penetrates. Now, these devices were quite rigid. It was a proof of concept demonstration. So it's interesting to do a bit more work on this and figure out where the limits lie. So we developed this interdigitated arrays. The full structure is shown here. These are a couple of millimeters long and wide, and they have interdigitated fingers that are coated, the fingers only, with P.PSS. The process here for fabrication includes just typical lithography on top of a stack that is parallel C, SU8, PDMS, and then parallel C. And we found this to provide a very good compromise between mechanical properties that allow handling and low thickness that allows a very good conformability. And then at the end of the day, this device is placed on adhesive medical tape. This is the white background that you see here, and attached to the skin. So here, if you put P.PSS on the gold electrodes, you lower the voltage that's required to inject a given current in the skin, so the device is safer. This also allows a larger range of currents to be injected at keeping the voltage below what is recommended by the clinic, which is 400 volts, 450 volts, and adds flexibility to the device. So the question is, are these electrodes selective? And to answer this, we use the following protocol. We developed this electrode shown here. So here is the backing tape that attaches them to the skin, and compare them with conventional cutaneous electrodes. So if everything I told you so far is correct, these electrodes will provide unspecific stimulation, will stimulate deep into the skin and excite many receptors, while this electrode will only stimulate small fibers close to the surface. So we apply them either on the foot or on the arm, and stimulate using a clinically approved stimulator at different configurations. And what we expect is that there will be a difference in response time. As unselective electrodes stimulate deeper, they stimulate larger fibers that conduct faster. So the stimulus here is expected to arrive faster to the brain than the stimulus from these electrodes. So we geared the setup where we can measure reaction time. Upon stimulation, the volunteer is asked to press a button when they get the sensation of stimulation. And then we start zapping volunteers. And we see that, as shown here, that the response time for the reaction time, as it's called, for stimulation with the commercial electrodes is faster than with the interdigitated array, both in the hand and on the foot, which again strongly implies that we're only stimulating the very thin fibers close to the skin. And again, we find here that globally stimulation in the hand is associated with a shorter reaction time than stimulation in the foot, which is correct according to what we know about the anatomy. It takes longer from the stimulus to go from the foot to the brain than from the hand to the brain. So this strongly hints to the localization of the stimulation, very shallow area to the skin. And this is an additional experiment that goes to show that indeed, if you passivate this, if you destroy this small nerve fibers, then you need to stimulate much harder in order for a stimulus to be perceived. So we use here a capsaicin model, which is a molecule that comes from red peppers, in order to temporarily kill nerve fibers, the small nerve fibers on the skin of volunteers. And then we measure the threshold current that is needed for the volunteer to register stimulation. Before capsaicin is administered, then both the commercial and the interdigitated arrays, the commercial electrodes, which are unselective, and the interdigitated array, have a fairly similar stimulation threshold. However, upon capsaicin administration, and this was administered for 3 days, 4 days a week, then you see that the commercial electrodes, which provide unspecific stimulation, have a similar stimulation threshold. And again, the idea here is that because they stimulate deep in the skin, they always find fibers to stimulate that were not affected by capsaicin. While stimulation with the interdigitated arrays, here shown on 2 volunteers, require a much larger threshold than before in order to elicit a response. Again, consistent with the fact that stimulation is localized. So this is a very convenient way now of interrogating these small fibers with a simple wearable. And we hope to be able to push this now to patients on its way to commercializing this technology and making it available to patients with small fiber neuropathies. Now, in the last few minutes, I want to talk about going beyond electrodes and whether and what would be the benefits of doing that. Here, I want to start by painting a very simple picture based on signal to noise. When we record with an electrode biological activity, say you're recording epileptic seizures, you're recording both the signal, which would be the seizure activity in this case, and the noise that comes from the brain. This is recordings from networks that are not affected by the seizure. And in this context, that would be the so-called biological noise. Then on your way to amplifier, you pick up some noise on the line, on the transmission line, because it acts as an antenna and picks up disturbances from cell phone towers, anesthesia equipment, what have you. So when you amplify all these components, including the external noise. Now, if you were to move your transducer to the point of acquisition, then you would amplify signal and biological noise, but you would not amplify the line noise. And this ends up giving you a better signal to noise ratio because you just do not amplify this component. Very simple argument, but it shows the essence of what we're doing. In a sense, you want to amplify as quickly, as close to the source as possible. A transducer that has been used for doing this is the organic electrochemical transistor. It offers a lot of advantages for biological transduction. This consists of a conducting polymer electrode we make them with P.PSS, and we take advantage of the fact that if you have an electrolyte, ions from the electrolyte can go directly into the polymer film and change its doping state. So here, this is interrogated by having a voltage applied between a source and drain electrode and measuring the whole current that flows through the channel. In a sense, this reflects the amount of ions that can go from the electrolyte into the polymer or vice versa. So it reflects the doping state of the polymer. These transistors operate at low voltages and show very high transconductance. So here is the transfer curve that tells us how much the current that you measure, the whole current, changes when a voltage appears in the electrolyte. And you want this curve to be as steep as possible. And in these transistors, it is very steep. So it's associated with, this is the first derivative, which is the transconductance, with transconductances that are very easily in the millisiemens range for small transistors. We have used those to conduct brain recordings, so electroencephalography. And these are some old data shown here where you wire two transistors to do a two electrode type of measurement of alpha rhythm. We use a transistor with a thick channel and a transistor with a thin channel. So you have a trade-off here. As I mentioned earlier, the thicker you make the channel, the thicker you make the conducting polymer film, the more interaction you have between the electronic and the ionic charges. And in transistors, this corresponds to a higher transconductance. This leads to a higher transconductance. If you pay a penalty for this, the transistor gets slower, so the bandwidth of the transistor decreases. If you use a thin channel, then the transconductance decreases, but the bandwidth increases. You push to higher speeds of operation. Now, for most wearable applications, we are looking at quite low frequency content. For example, the alpha rhythm is around 10 hertz. So here you can trade unnecessary bandwidth for better transconductance and end up having much higher quality recordings, as shown by the power, the difference in the power of the signal between these two recordings, that you can adjust by playing with the thickness of the polymer. So again, this mixed conduction gives you a new degree of freedom. In electrodes, you get lower impedance by making the polymer film thicker. Here you get a higher transconductance, and both lead to higher signal-to-noise ratio. So great for electrophysiology, but you can go beyond that with a transistor. This is an old paper where we added an enzyme called glucose oxidase, and then some glucose in the solution. And when glucose and glucose oxidase are present in the same media, that leads to the generation of peroxide that can then be decomposed at the appropriate gate to hydrogen and oxygen. And this yields an electron that contributes to gate current in the transistor. So that gate current then changes the drain current, is responsible for getting ions into the channel, and that changes the drain current, giving you a response that depends on glucose concentration. And here again, the transistor can give you amplification by applying a higher gate voltage. You have a crank that you turn up, and the steepness of the response of the calibration curve, if you wish, becomes higher, so the device becomes more sensitive. The mechanism of operation here is that you set up a potential difference between the gate and the electrolyte, and between the electrolyte and the channel. So if you look at the potential, you have the gate at a different potential than the channel, and the electrolyte is somewhere in between. And if you enable this enzymatic reaction and start collecting current here, that decreases the voltage drop between the gate and the electrolyte as a result of this current, and that gives you a higher potential at this interface that drives ions in and changes the drain current. So we have been working on these transistors since the first paper, and now we can make them very small, of the order of tens of microns. I'm sorry, I'm missing a scale here, of the order of tens of microns in terms of their channel, and couple them with gates onto which we mobilize the enzyme in an appropriate polymer. And we also induce platinum nanoparticles that are excellent at converting this peroxide to a gate current. And with this, we can now measure small steps during the physiological limit in different biological fluids. You can also turn these transistors into ion sensors. Again, this is work we did a while ago, where we used ion selective membranes to control which ions interact with the channel. And we can change the behavior of the transistor in a fashion that reflects the ion concentration at the other side of the membrane. In this early work, we had used the hydrogel here, which is great for demonstrations and for understanding how the device works, but technologically imposes a lot of limitations. We since then replaced that hydrogel with a solid electrolyte, PSS sodium, and this allowed us to miniaturize these devices. We can make them again tens of microns in dimensions and obtain excellent performance. So here with a sodium sensitive membrane, you can see good reproducibility, good range of response, and quite fast response of the order of a second with these miniaturized transistors. So they offer a large range, they're reproducible, they're fast, and also show Super-Nernstian response. This has to do with the architecture of the device and the ratio of capacitances as you project what happens to the membrane to what happens to the channel. You can also use different membranes to be sensitive to other ions, such as potassium or pH. You can use membranes that make your transistors sensitive to protons. And these also show very good stability. After storage for 5 months, the response changes very little. So with that, let me start wrapping up. What I've shown you is that conducting polymer electrodes, such as the ones made of P.PSS, allow high spatial resolution EMG recordings. We haven't reached the limit. Higher resolution than millimeter electrode seems to be possible. We're working on this. We're also applying the same to the heart and to the brain. If you ask people who work on EEG, for example, they'll tell you that the spatial resolution of EEG is about 1 centimeter. This is based on the distance between the skull and the cortex in a typical human. However, I think this strongly depends on electrode technology. And we know for a fact that even millimeter type of electrodes will be able to record spatially different, placed millimeters apart, spatially different information. So this whole area of what is the ultimate spatial resolution needs to be revisited. We talked about controlling the depth of stimulation. There is an elegant way to do this by using interdigitated electrodes, as proposed first by the Italian group I cited. Here we use P.PSS to increase the safety of the device, decrease the voltage that it's required to inject the current. And we demonstrated that indeed experimentally, this is a good way to do diagnosis of small fiber neuropathy and to monitor the progression of the disease. So we have high hopes for commercialization of this device. And then I talked about transistors. This is a long effort in my group that spans several years. We have shown them to be a powerful transducer for cutaneous electrophysiology, especially given the low frequency regime, which is of interest to most wearable sensing. You can also make ion and metabolite sensors by using ion-sensitive membranes and enzymes. And this has been maturing through the years to the point where today they're robust, reproducible. They offer a good gamut of things that you can sense. And it's now a good time to integrate them in multimodal systems where you can do both biological and electrophysiological analysis of someone's health by using the skin. So let me thank my co-workers, Sangil Han, Ivan Dimov, Scott Keen, Eleni Mitudi, and Santi Velasco, all of whom are engineers who are developing these technologies. We get some of the materials from, I forgot to highlight, David Mesereyes and Oren Sherman. And a lot of the applications are informed with from collaborators from either clinical neurosciences or medicine, Manohar Bans and Michael Lee. So with that, let me thank you again for your kind invitation. I think I left 3 minutes or so for questions. It's a pleasure to be with you.
Yes, sir. So Malliaras, here. So thank you very much for the talk. So, and also thank you for planning our future. So I have two questions actually. So the first one is for the study of the stimulation depth, how do you measure the response time? So how it is measured? And my
yes, please go ahead.
Yeah, my second question is that can you elaborate further why high transconductance can increase the signal-to-noise ratio?
Yeah, thank you for these questions, both very relevant. The way we measure stimulation is by using reaction time measurements. We found this to be the most convenient from a clinical perspective. Another way to measure it is to use EEG and try to catch the evoked potential when it arrives on the brain. This probably will lead to a tighter distribution in the error bar here in the data. But experimentally, it's much less convenient to implement and more expensive. You would need to have an EEG set. The nurse would need to come in to apply the EEG set to the patient, fill in the cup electrodes with electrolyte. The examination would take longer. There are limits in people who have long and thick hair. So experimentally, it's much more convenient to just have a button that the volunteer presses to register the reaction time. Again, they do not know when the stimulation is sent. The computer keeps track of that and keeps track of the response time. When they feel the stimulation, they press a button and that reaction time is getting registered. On the second question of why we increase signal to noise ratio is because we increase the power of the signal. So if you how do I do this? So yeah, if, for example, you can set up an experiment where you put a little modulation here in the gate of the transistor, an AC signal, and measure then the power in the circuit, and then the power in that circuit. So a little voltage modulation will increase an AC current at the gate. That will increase an AC current at the drain. And by multiplying current and voltage here, current and voltage there, you can get the power of the signals. And that correlates with transconductance. You can show that the higher the transconductance, the higher the power of the signal. So by how much it will increase the signal to noise ratio, it depends on how much noise you have from the external environment. Because that is additional noise that doesn't get amplified. Back to this idea here. In a typical situation in the clinic where you have a cable that's of the order of a meter or more, which is very typical in any clinical scenario that we've seen, that makes a big difference.
Yeah, got it. Thank you very much. Yeah.
Very welcome.
Okay, so the chair, Professor Feng Yan, has one question.
Hi, George.
Hi.
It's Feng Yan. Thank you very much for giving the keynote speech. I have one question about the polymer device. Here it shows the PSS to be a very good material for the electrode, right? For to get a good contact with human body, right? So is there any, besides the PSS, what is a critical issue for this type of applications? For example, what is the ion transfer or the conductivity of the material are critical? What is?
It's a very good question, Feng Yang, and the answer is I don't really know, to be honest. For me, it's difficult to decouple the mechanics of the contact with the impedance. You obviously need good attachment to the skin, good mechanics, before you can measure a low impedance. But also, assuming that you have good mechanics, say you press an electrode well to the skin and it conforms well, different electrodes perform differently, which means that the nature of the electrode also plays a big role. In PDOT, and again, we have mostly experience with PDOT, we find that if you treat the material with, for example, impregnated with ionic liquids, you end up showing a better impedance, even with nominally similar mechanics. So again, you have a PDOT film, you have a PDOT film with ionic liquid, you press them both against the skin. The one with ionic liquids will give you a lower impedance. So there is something to be said about trying to get a bit better contact by modifying the material. And ionic liquids offer a very useful way of doing this. Gels can also help. Having a gel in the PDOT or making PDOT into a gel will also help. But again, there is always the consideration of, does it only help the electrical or also help the mechanics of the contact? And that's very difficult to decouple.
Okay, thank you. Thank you very much, George.